last time I discussed the path from Eulerian, Q-Eulerian polynomials to chromatic quasi-symmetric functions. So we started with the Q analog of the Eulerian polynomials. We lifted it up to a symmetric function that we called the Eulerian quasi-symmetric functions. And then we applied an observation of Stanley's that omega of the Eulerian quasi-symmetric functions is the same as the Smirnov word enumerator, with a Smirnov word enumerator is defined and these were words over the alphabet, positive integers with no adjacent repeats.
Michelle, I assume the sigma and the W are actually the same thing, is it?
Oh yeah, thank you.
Sure.
And the W is different from the omega. I don't know how to make it look different, but okay. So those are the Smirnov words and of 1,000. Okay. And then we observe that this is the same as the set of, as the proper coloring enumerator, XC T to the descent of C. And that's also the same because we can read from right to left instead of from left to right. T to the ascent. The Pn was the path. The descent of a coloring and the ascent. And then this led to generalizing this to all graphs. Why stick with just the path graph? So that led to the chromatic quasi-symmetric function. C is coloring of any graph, these are proper colorings of any graph, and we chose to use the ascent formulation. And this is a quasi-symmetric function over the ring of polynomials in T. And just to review, the ascent set of C of a coloring is the number of edges where I is less than J, and the color of I is less than the color of J. So the coloring order is consistent with the edge, with the vertex order. And the descent and now the coloring order is the opposite. And then, okay, and it turns out that when this is symmetric, then it doesn't matter if we use ascent or descent. And so that follows from the following proposition. If xg, xt is symmetric, and I mean symmetric in X, then T to the number of edges of G, X of G, xt inverse is equal to xg, xt. So this implies xg of xt is palindromic, because here we're just reversing the coefficients. So that implies that this is palindromic. And this expression is using the des, and this one we're using as. So this is saying that they're symmetric, that they give the same symmetric function. So it's because of that proposition. Okay, so that was the first thing to observe. And the question is, when is this symmetric? Okay. And over here, by palindromic, I mean as a polynomial in T. Okay. So when is it symmetric? So the answer is whenever, well, I don't have the full answer, but whenever G is a natural unit interval graph. So that's the same as the incomparability graph, where P is a natural unit interval order. What the graph can also be thought of as if you take unit intervals on the real line, on the say the positive real say part of the real line, and you look at unit intervals and you say that there's an edge between two unit intervals if they intersect, and the order, the labeling on the unit intervals is left to right according to left endpoints or right endpoints. So it can be described in terms of unit intervals. So that's symmetric when it's a natural unit interval graph. And it's also another example of symmetric is when it's a naturally labeled cycle. So here's the graph. And I'll call that Cn is the cycle. And this, this was done by, this was shown that it's symmetric by Shureshian and myself. And this was shown by my former student, Brittany Elsie, and myself, that you get symmetric. And I don't know, maybe someone else does, but I don't know of any other examples in which you get a symmetric chromatic quasi-symmetric function. I don't know, it would be, I don't know how to generalize. We will see a way to generalize that, but then we have to generalize the definition of chromatic quasi-symmetric function. But just with this definition, I don't see any other examples. I don't know of any other examples.
Michelle?
Yes.
So the way you can think of the natural unit interval graphs, another way of thinking about them is, of course, you're taking complete graphs and pasting them together along complete graphs in a
Right,
line. Did you try
right.
pasting together cycles?
Yeah, it's similar thing works for cycles.
Oh, it does.
Okay.
So that's
Where,
another family then. So
yeah, where you're going around in a circle with complete graphs and not. Yeah, but it does. I shouldn't have said it works because it doesn't give. No, it does not give us a symmetric. I
that was
was
my question. That was my
what?
question.
Yeah, your question. Yes, something more general. I'll talk about that in the next lecture. A more general version of the definition of chromatic quasi-symmetric function than what you suggested does work for that more general
Okay, interesting.
definition,
Cool.
but not with the current definition. So if I were to do something like this, add edges, I think this is add edges like this, like
Mm-hmm.
that.
That
That
doesn't.
doesn't work.
Okay. Okay, interesting. Thanks.
Okay. And oh, I wasn't quite telling the truth because any graph with connected components, this is just true for as above. So you could have cycles and paths and all kinds of things as above. So if the connected components of a graph are one of these, then it's symmetric. Because the chromatic quasi-symmetric function of the component, when you multiply together these chromatic quasi-symmetric functions of the components, you get the chromatic quasi-symmetric function of the graph. So we can really just talk about connected graphs. So the formula from last time, so that's the generating function for the elementary symmetric functions. That formula has the following consequences. It's not hard to show that this implies that xpn is E positive from that formula and E unimodal. So when John was in John's lectures, he talked about E positivity, but not that much about E unimodality. And so by that we mean for all, it's also palindromic, but that's easy to prove without this formula. That when you go up to the middle and you take the coefficient of t to the j plus 1 minus the coefficient of t to the j, so that's going to be a symmetric function. When that's E positive, that's what we mean by E unimodal. So the coefficients are increasing in a sense because their differences are E positive. And from that formula, we can also prove not just E positivity, but E unimodality. And the other consequence of this formula is that the Frobenius characteristic of the representation on the cohomology of the toric variety associated with the dual permutahedron. Tensored with the sign. Is XPN. So this is graded. The representation is graded, and the Frobenius characteristic of it is the chromatic quasisymmetric function of the path. So how do we get that from this formula? Well, we get it from this formula because of a result of Procesi and Stanley. They proved that the Frobenius characteristic is equal to this with H's instead of E's. So their formula tells us that this is true. So they got this for the Frobenius characteristic, the generating function of the Frobenius characteristic. And since John and I proved this, we know now that that is the same as the Frobenius characteristic. That's why this claim holds. So these two properties are what led to our conjectures that
Michelle,
yes.
so there's a question in the chat.
Uh-huh.
Do Procesi and Stanley have a cohomological interpretation of the H positive version?
Yes, it's of the H positive version because they don't tend because of this. I'm saying, so I could have actually, I could get rid of this and just say this. That's what I should have said. Okay. So they proved this formula with H's. They proved that this is the generating function for the Frobenius characteristic of that representation. And so our result combined with their result gives this consequence. So conjecture one is the refinement of Stanley, Stembridge. If G is a natural unit interval graph, then XG XT is E positive and E unimodal. And so that generalizes this first consequence. Oops. That generalizes this. And then we also have a conjecture that generalizes this. And that was the connection with Hessenberg varieties that John talked about. And that's now proved by Brosnan and Chow and Gay-Paquet. So that's what John talked about in his talk, in his lectures. So these two conjectures came from the properties that we knew were true for the Smirnov word enumerator. So I'm going to focus on conjecture 1. So consequences of conjecture 1. Well, John talked about sure positivity. E-positivity implies sure positivity. So that would be evidence that, some evidence of E-positivity. So John talked about a proof involving p-tableau. The other consequence of conjecture 1 is sure unimodality. So the difference of the coefficients is sure positive. Okay, this follows actually from conjecture 2. So I shouldn't. This is from conjecture 1. And this follows from conjecture 2. It's a consequence of conjecture 2. So when we first were working on this, we knew that sure positivity was true, but we didn't have a proof of sure unimodality. We knew that it followed from conjecture 2 and the Hard-Lefschetz theorem. So that's how I don't want to go into the details on that, but that's how we get sure unimodality, which now we know is conjecture 2 is true. So we get sure unimodality. So here's
pardon me, Michelle.
Yes.
For sure unimodality with Hard-Lefschetz, you need the manifold to be smooth and compact, right? So are Hessenberg varieties, are the regular semi-simple ones smooth or?
Yes, I'm not, someone else might know this better than I do, but yes, I believe. I don't know. I mean, I think so.
All right,
but it definitely applies.
Oh, all right. Thank you. I'm sorry.
Yeah. I can actually see who's talking. Why don't I?
It's Brendan. Hi.
Oh, hi, Brendan. I don't know. Oh, yeah. Okay. Then, hi. So here's a problem. Find a combinatorial proof. Unimodality. That doesn't require me to answer Brendan's question. We don't need the Hard-Lefschetz theorem or conjecture 2 if we had a combinatorial proof of unimodality, of sure unimodality. Sorry. That involves p-tableau. That's what John talked about. So this is purely combinatorial.
Michelle?
Yes.
Sometimes to prove something combinatorially is unimodal, it's actually easier to prove that it's log concave combinatorially and then get the unimodality as a consequence. Do you know whether it's sure log concave or not?
For the path, we have conjectures that it is. Gotcha. We tested that on the computer, but I'm not sure. I don't think we've tested beyond that.
Aha.
So,
Okay.
but that's a good question.
Right. Okay.
So the third consequence of E-unimodality is that P positivity I'm sorry. And P unimodality of omega, because that this being E positive would imply that this is P positive. So this okay, so that's the third consequence. And so the question is this true? Is it P positive at P unimodal? That's the third consequence of our first conjecture. So in the case T equals 1, Stanley proved it is P positive. So this was the result that Stanley obtained for all graphs. And now all graphs, every graph, there's no restriction on the graph. So this is the Mobius function. This is the bond lattice of the graph. And we're taking the Mobius function on the bond lattice and the type of, so the bond lattice is a sublattice of the partition lattice. The type of the partition is just the size of the blocks. So we get a number partition by taking the type of a set partition. And this is the power sum symmetric function. I should have said that here. That's what the P stands for. And so from this, well, the Mobius function alternates in sign. And so that tells us that xg, x1 is P positive. Okay. The Mobius function for the bond lattice alternates in sign, and by applying, omega. By applying omega, we get P positivity. Okay, we'd like to do this for general T, conclude P positivity. I don't know a way to generalize this very nice, this very pretty result involving bond lattice, but we found some other way to expand when there's a general T here in the power sum symmetric functions. And so let me describe our approach. Let's forget the omega. Okay.
Michelle?
Yes.
This is Teodros. I want to ask, in your previous statement of Stanley, the computation is t equal to 1. And now, what if you put, instead of 1, -1, would you be able to avoid the alternating signs in the Mobius, or Is there anything known?
That I don't, I have to think about what happens when you put -1. We could, I can't think about it right now. It's,
It's okay.
yeah. We may have a simple answer to that. I can't think of it now. Maybe someone else knows. Okay, so I need to describe some terminology now. Let P be a poset on N. A word A1 to AK over alphabet N has a P descent. So that's what I'm defining now, P descent. Although John talked about P descents too, at I, if AI is greater than AI plus 1 in the poset. Okay, we call it a P descent. And the other thing I wanted to, so I wanted to define P descent, and it has left to right, P maximum at I, if AI is bigger than AJ for all J less than I. And I want to say that I is bigger than 1, because of course, if I is 1, it's always, so I want non-trivial left to right P maximum. So I'm requiring I to be bigger than 1. So everything to the left of it is smaller than that letter in the order given by P. And now we're going to let NP be the set of all sigma in Sn such that sigma has no P descents and no left to right. P maximums. Okay, so let's do an example. P could be any post set, but I'll do this particular post set. And let's take the permutation 2, 1, 5, 4, 3, 6. So the permutation's a word when we write it in one-line notation. Okay, so does this belong to NP? Well, let's see. We have an ordinary descent 2, 1, but that's not, this is not a P descent because 2 is not bigger than 1. So that's not causing any harm. So, and that is not a P descent. So I got rid of it. Let's go to the next descent. I should make it smaller. So 5, 4. Is that a P descent? No. 5 is not bigger than 4 in the partial order. So that's not a descent either. 4, 3. No, 4 is not bigger than 3. And so there are no P descents. And so what about the second condition? that it has no left to right P maxima? Well, 1, 5, we come to 5. That is a P maximum because 5 is bigger than 1 in the post set, and 5 is bigger than 2 in the post set. So 5 is bigger in the post set than all the previous letters of the word. So the answer is no. Okay, so that's not in there. And I can do another one. This time, if we look at this pair, there is a P descent there because 5 is bigger than 2 in the post set. So that also does not belong to NP. This one does not belong and that does not belong. Here's one that does. Okay, so all the descents that you see, they're not P descents. This is not a P descent. This is not a, I'm sorry, that's not a descent at all. That's not a P descent, not a P descent, not a P descent, and that's not a P descent. So, and there's every left to right maximum, 5 is, but it's not a P, a left to right P maximum because 5 is not bigger than 4. So it's not a P maximum. And the same for 6. It's not a P maximum because 6 is not bigger than 5 in the post set. So it has neither. That makes it belong to NP. Oops, sorry. So that one does. So John and I proved let G be the incomparability graph. Natural unit interval order. So that makes G a natural unit interval graph. The coefficient of 1 over n Pn, Pn, I could have just written Pn in the power some expansion of omega is NP. You sum over all permutations that have no P descent and no left to right maximum, and you take T to the number of G inversions. And a G inversion is a regular inversion that forms an edge of the graph. So that gives a combinatorial description of the coefficient of 1 over NPV. And this actually can be simplified to something else, but I want to write it in this form because this is what suggested the general formula that we have for 1 over Z lambda, P lambda. So and the way we proved this is we used our expansion in the Schur basis in terms of P tableau, And then we use the Murnaghan-Nakayama rule and some bijections and sign reversing involutions, and we ended up with this. There are other ways to prove this, but that's how we did it. But this result led to a conjecture for the coefficient of Z lambda inverse P lambda in the expansion. So to tell you what that is, I need some more terminology. So given a poset P on N and a partition of N, let NP lambda, so now I'm generalizing the notion of NP, be the set of fillings of the Young diagram lambda, associated with lambda, with the entries 1 through N, used once each, so that the rows have no P descent and no left to right. P maximum. So if the length of lambda is 1, then we're just talking about permutations in NP. So this is like P tableau, only there's no condition on the columns. Okay, and when we were talking about P tableau, we required no P descent in the columns. Now we're talking about no P descent in the rows, and we have this extra condition that there's no left to right P maximum. So since there's no condition on the columns, what we're really doing is looking at permutations that we're splitting according to lambda, and then looking at the segments of the permutation and imposing conditions on the segments of the permutation. But I think it's convenient to do it in terms of tableau. So let me say this again. If the length of lambda is 1, then NP lambda is just the same as NP. So that generalizes that class NP of permutations. So let's look at an example. The example we used before, 1, 3, 5. Two, 4, 6. Okay, and lambda now, let that be 3, 2, 1. So that's a partition of 6. And so I need to fill in the shape 3, 2, 1. And then check that each row has no P descent and no left to right P maximum. And you can see there's no P descent in the first row because 4 is not bigger than 3 and 3 is not bigger than 2 in the post set. Same with the second row and the last row. And there's no left to right P maximum. So this is in NP lambda. Okay, any questions? So here's the general conjecture. which was proved by Athanasiadis. Let G be the incomparability graph. Then the coefficient of Z and let lambda be a partition of n. Then the coefficient of Z lambda inverse P lambda. I'm sorry, there are two P's here. One's capital and one's lowercase. It's hard to tell, but in the power sum expansion of omega xg t is, now t is in the set of tableau of shape lambda, t in G, and then just take the row word of t, which is really, so this is really a statement about these permutations that you partition according to lambda. And so row word of t is that permutation. You read the rows of t. Row word is the permutation in Sn obtained by reading t in row order. So, okay. So let's look at an example of this theorem. P and G. So this is a natural unit interval order, and it gives us the incomparability graph of this is just the path. And let's let lambda equal 2, 2. So n p lambda is the set. I will list all the tableau in there. So that's 1, 2, 3, 4. Then 1, 2, 4, 3. That's okay because the descent is not a descent of p, 4, 3. Then 2, 1, 3, 4, 2, 1, 4, 3. There's no relationship between along the column, so we're just checking the rows. 3, 4, 1, 2. We can switch the rows. It's still good. 3, 4, 2, 1. So I'm going to copy these 4 rows by switching those 2 rows. 3, 4, 2, 1, and then oh, I didn't do that. 4, 3. 1, 2, and then 3, 4. 2, 1, 3, 4. 4, 3, sorry. 2, 1. And that's it. Those are all of them. And then I need to find the number of inversions of the row word of each of these. So the row word of the first tableau, that's 1, 2, 3, 4, that has 0 G inversions. 1, 2, 4, 3 has a G inversion here, 4, 3. So there's 1. 2, 1, 3, 4 has the G inversion 2, 1. There's 1. We're counting G inversions. 2, 1, 4, 3, there's 2. 3, 4, 1, 2, there's none. Oh no, there's none. 4, 3, 1, 2, there's 1. 3, 4, 2, 1. The word 3, 4, 2, 1 has, see, I think I'm not doing this right. 1, 1, 2. This should have been. Three, here the versions are 3, 2, and, oh, that is correct. That's just 1. Now here the inversions are 4, 3, and 3, 2, so there are 2. Here the inversions are, here there's a 2 again, and here there's 3. So the coefficient, T, row word, 1, there's t to the 0, there's 3 times t to the 1, there's 3 times t squared, and there's 3 times, and there's 1 times 3 cubed.
Michelle, I'm confused. Can you help me? For the 3, 4, 1, 2 tableau, the fifth one in, when the row word is 3, 4, 1, 2.
Oh my goodness. Okay, yes.
So 3, 4, and 1, 2 are definitely not inversions, and 4, 1 isn't an inversion either because there's no edge between 1 and 4. Or am I missing something?
Right. So 3, 2 is the inversion there. 3, 2.
Oh, that's right. They don't have to be adjacent. They don't have to be adjacent. Gotcha. Gotcha.
Right.
Yeah. Okay. Thanks.
Thank you for asking that. So that so those are the G inversions. So that depends on G. The tableau themselves depends on P. But G is the, so this is, but G is the incomparability graph of P. So we get this. And note, this polynomial is palindromic and unimodal. And that has to be true. This is P unimodality. If our conjecture is correct, and this has to be true, of omega x g x t implies that all the coefficients of the power sum symmetric functions are palindromic and unimodal. And here, these are the coefficients according to the theorem. It's unimodal, not p unimodal. This is a polynomial in T. This has to be unimodal. So if this is p unimodal, then this has to be unimodal. Actually, knowing this it's equivalent. So the unimodality of that polynomial implies the p unimodality of this, which the general conjecture tells us has to be true. But this is still open. We don't have a proof that this is P unimodal, and this would be a combinatorial approach to showing that it's P unimodal, just to show that that polynomial for all lambda is unimodal. And it is in this case. And that's because here G is the path, and the path we know is E unimodal. So it's P unimodal.
Michelle?
Yes.
This is Theodorus again. And is there any count on the cardinality of NP lambda for any lambda?
Again, I can't answer right away. I mean, it's not something I thought of. I don't know how hard it is to count it. So, but good question. I don't know.
Yeah, that's just T equal to 1, you know.
Yeah, just to count NP without the lambda, just counting NP. Right, right. Oh, yeah. So we should be able to do that. Yeah. Okay. So I want to talk about Athanasiadis's proof of the theorem. So Athanasiadis just proved P positivity, not P unimodality. And I'm not going to have time. I'll talk about that next time. I ran out of time. Okay, I'll discuss how he proved this conjecture. So, thank you.
Thank you so much.
Thank you.
Nice talk. Any questions for Michelle?
Sure. Well, that was a great talk, Michelle. This is Brendan, by the way. So sorry to ask another non-combinatorial question, but for the cycle, for the directed cycle, do you have? So I guess you have E positivity and E unimodality in that case too. Is there any connection with like representation theory or geometry that's known there?
No. I mean, so the cycle, the labeled cycle.
The labeled, naturally labeled cycle.
Naturally labeled cycle. No, that we have when n is even, or I forget if it's even or odd, when n is even, we have the it's always E positive. We have the unimodality when n is even, but when it's odd, we have to add, I might have even and odd switched, but we have to add a simple term to the middle coefficient in order to get it to be unimodal. So with a slight modification, it becomes E unimodal. So yes, so we have a formula for that, which gives us all of that about that cycle, but no representation, theoretic interpretation. That would be nice.
All right, thank you.
Okay, thank you. Any other questions?
So I don't see any questions in the chat either. All right, so let's thank Michelle again.
Thank you. Thank you.
So have a nice weekend, everybody. I will upload the video on the YouTube and have the extended notes ready by this weekend. And I will see you all next week.
Bye.
Bye. Have a nice weekend.
You too, everyone. Thank you.